Hello everyone. Who's here with me today? I'm going to start where we left off, the problems I asked you to look at, to attempt overnight. And we begin with an example. The question being, is this setting that which defines a binomial random variable? So what we need to do with this problem, if you've attempted it, is determine whether the three criteria are satisfied for this phenomenon. So what is it? Let's read through this. In a test of ESP, so that's extra sensory perception or telepathy, the experimenter looks at cards that are hidden from the subject. Each card contains either a star, circle, wavy line, or square. Really important that there's 4 options. So let's highlight that. Okay. An experiment looks at each of 100 cards, let's underline that, in turn, and the subject tries to read the experimenter's mind and name the shape on each card. Okay, so the person, there's the subject, and then there's the experimenter. The experimenter holds a card without showing the face of the card, the image, and asks the person, the subject, to basically guess what the card is. Now, if this person guesses right enough times, we have to set by previous experimentation or some sort of notion that it's not just chance luck that he's guessing right. And we establish in advance that if a subject gets 50 correct, they will have demonstrated that they have ESP. So what are we looking for? We're looking for, well, that's a good question. What are we looking for? What is the success? So that's the main question. That's what you're going to have to be able to determine on your own in order to determine if you have a binomial setting. I wrote it here. This statement shows you that your variable, that you define it as x, as the number of successes in n trials, and they have to be independent trials. If a variable is counting, it's a count variable, so it's discrete. It's counting the number of successes starting at 0, meaning no success, to up to all successes being n successes. Since I've told you this right away, the way that it's laid out, a success is a correct guess. A correct guess each time is what I'm interested in as the success, correct guess. So the word success corresponds to in this case a correct guess. Okay, so that's a success. He got it right this time. Then you're going to try again. You're going to show him another image without telling him his success rate. Doing this how many times? 100 times. You're going to ask him again, what is the image on the card, without showing him the face. So the subject has to respond, stating one of these alternatives. And if he gets it right, we observe again it's a correct guess. If he gets it wrong, it's a failure or incorrect guess. What I'm interested overall is out of all 100 attempts, how many total did he get correct? That's what the that's what this answers. That's what this variable answers, and that's the variable here, the number of correct guesses. And you always have to say out of how many trials. I didn't write it there, but I was just trying to give you the successes, just to get you motivated, get you started. All right, so what have we determined? Let's see if we can satisfy the criteria. In the first case, yes, it's true that a success and a failure are complementary and the only possible outcomes, okay? So either they got a correct guess, success, or failure would be incorrect guess. Number 2, do we know P? P is defined as the probability of a success each time. Do we know that? Okay, let's look back. I didn't say this is P, but I gave you some information, and from there you can gather there's 4 possibilities. Since the person's just guessing, because we don't know they have ESP yet, right? So we assume that they don't, or we don't know, but we have to proceed imagining that they just guess. So they guess. There's 4 possibilities. If they're just guessing, there's 4 possibilities, and we know from probability rule number 2, that all the possible outcomes, the probabilities of those need to sum to 1. So since they're equally likely, there's 4 equally likely outcomes, because he's just guessing, right? So there's 4 equally likely outcomes. There's no reason for him to think at any given point that one image is more likely than the other image. And the way that this would work is every time the cards are shown, the experimenter should be starting with a fresh deck of cards, all right? So the chances are equivalent in each try. You know, it's always going to be what each try for them to be equal, and there's 4 equally likely outcomes. That means the P must be 1/4 or 25%. Okay. Why again? Because there's 4 possible outcomes, all of them equally likely, and they need to sum. So they need to sum to 1. So the only thing that's going to satisfy that is that they're all 1/4. So 1/4 plus 1/4 plus 1/4 plus 1/4 is 1. All right. So next, what are the number of independent trials? So there's 2 things here. You need to know the number, which we're going to call n, and you need to know that they're independent. What does independent mean? Independent means, in this scenario, from each attempt, the chance of the person getting the correct card is going to be (1/4), and the next time, the chance of correcting, or the second time, the next chance of correctly guessing doesn't change. It's still 1/4, and the next time, the chance of him getting a correct card doesn't change. It's still 1/4. Okay, so each time he's guessing, it doesn't matter which, if it's the first try, the second try, the 100th try, the chance of getting it right is always 1/4. Since that stays the same, we know that trials are independent. No matter what happened on each try, the probability of getting it right stays the same. So n is going to be 100, and there are 100 independent trials. Right, so yes, this is a binomial setting, and the variable that we're interested in, which I should spell out, even though it's above, I'll spell it out again. So since we can write x, big X, right, because that's the variable, x is equal to the number of correct guesses in 100 trials, independent trials. Let's write it. I'm going to just say independent trials. So when I write IND, you know what that is. All right, and the possible numbers that they could be, it could take on, it could either be no successful guesses in 100, 1 successful guess, 2, up to 50, 51, all the way to 100, okay? So I'm just showing you, that's 51, all the possibilities. Those are the possible outcomes. How many possible outcomes are there? In fact, there's 100. Oh, you guys can't see that. Let me move it up. This is always the case for the binomial. How many possible outcomes are there? None. All the way through 100. That means there's 101 possible outcomes. It's always one more than the number of trials. Okay. Okay, so this is a binomial with parameters n and p. So we write x is binomial. N, remember alphabetical order, so you write n as 100, and p is 1/4. Okay. All right, so how many of you got that right? Anybody get that right? Let's save it. Let's go to the next problem. So that was an example. The binomial variable is an example of a discrete distribution, of having a discrete distribution. Let me say one more thing about that before I continue. What's the chance, and this is a question that we're going to answer, what's the chance that a person has ESP? Well, from the word for, if you take if you go back and you read it, a person is known to have ESP if they have more than 50 correct guesses. This means implies that symbol. So more than 50 correct guesses means the subject has ESP. They can read minds. Okay? Telepathy. So how would we figure that out? what we really want is to use our knowledge that this is a binomial distribution, learn, I'm going to teach you how to set up the formula for identifying the answer to questions like this. The probability x greater than 50 is what you need to compute. All right? So to compute that, you would have to consider finding the probability of all the outcomes. Let me write this again. So what are the possible outcomes? 0, 1, 2, all the way to 50, 51, and then to 100. So what you need to do is you would have to find all of these, find the probability of 51 correct guesses, 52 correct guesses, 53, all the way to 100. You'd have to compute those with the formula that you're going to learn and sum them. And that would be the answer to this question. Now we don't have the tools yet for that, but we're going to get there, okay? That's our north. That's where we're headed to answer that question. Just keep that in mind. Okay. I'm going to save that. We're going to learn how to get there. But first, I want to review the problem. About a continuous type of distribution. The continuous type of distribution we discussed yesterday is the uniform distribution. Now I gave you some pointers about the uniform. As long as you know how to operate with density curves, shapes, basically finding the area under a curve is what we're interested in when the variable is continuous. Now the shape here is not like the normal distribution shape. The normal distribution shape was a bell-shaped curve, and to find the area we used a table. If you didn't have a table, you would have to use calculus and the formula for the shape to calculate the area under the curve. But luckily, we're going to give you a simple example. Here, it's a rectangle. The rectangle goes from a lower bound of -3 to an upper bound of 10. So that's all we have information about. And the fact that the variable x is uniform with those bounds. That's all we need. Since that's all we need, the lower and the upper bound is all we need. I need to list those as parameters. They're the characteristics from the population that describe the distribution for me so I can solve, so I can make estimates about what to expect. So here is the distribution. It's very simple, as I explained before. The way we interpret this is we say all possible outcomes are equally likely. Now, because it's continuous, all possible outcomes come in ranges. And so I give you some questions, or ask you some questions about ranges. In particular, what is the probability that x is greater than 5? Okay, let's plot this out. So let's say this is 10. So so let's say here is 0, and then here is 5, and there is 10. Okay, so that's just to divide up the line, sketching it maybe not perfectly to scale, but it gives you an idea. So what I want is the probability that x is greater than 5, where x is uniform. So I want this. And then I also want, what is the probability that x is negative? Okay, so what's negative? Anything over here is negative. But let's do them each one at a time. So let me take that off. Let's do this one first. So now, referring to the distribution, probability that x, you don't have to write it like this. If you just make a drawing for me, I'll be happy. Always happy with the drawings. X is greater than 5, where x is defined as uniform. The probability is, because it's just a square or rectangle, is going to be height times width, just that area, and it happens to be a rectangle, so height times width. Height, we need to find that, and width, we need to find that too. So what is height? Well, I'm remembering, and you can always do this from first principles, but you can also remember it with a formula. So area of the curve, well actually let's do this beside the curve. So over here, area is equal to 1 of the whole thing, not the blue part, just the whole density curve. So then area must be also the height times the width of the whole thing. Now this formula looks familiar from here to here, but I'm referring to different boxes, okay? You have to identify which widths I'm talking about. So for this one, for the entire thing, the height that I'm referring to is this one, which is just this one here. And the width I'm referring to is the whole width. And I explained to you last time, so don't forget, the way to compute a width, the width is always equal to upper end minus lower, okay? The higher end minus the lowest end. So for the width of the whole thing, we calculate that the width is equal to 10 minus 3. Can you see that? That's very badly done. Let's see. I'll try and move it closer. Width is equal to the upper minus the lower, which is 10 minus 3, which is 13. Now once you have the answer, it makes complete sense, right? It's bigger than 10 because it goes beyond 10. The width completely is 13. All right, so that's the width. So now with this information, I can find the height. So let's move all this down here. So then maybe I'll erase this statement here. No, I do want to find that. But this is the first step. So let me see if I can erase this. Just this for now. I just want this one. No, it's gonna erase everything. Ooh. I'll leave it. So for now, we're gonna say note area equals, the whole area equals height times width, means 1 is equal to height times 13. So height has to be height has to be 113. Right? So it doesn't look like that in my drawings, not to scale, but it's just an abstraction, a tool to help you see what I'm doing, the mechanics of what I'm doing. Doesn't look like it's the height is 113 if the other scale is so big, but anyway, on the vertical axis, height is 113. So for the whole box, height is 113. So I'm going to write that here. So since height is 113, now I'm going to use that height together with this width between here. So since height is equal to 113, now I can calculate the area of the blue box, and I'm going to refer to it as the probability x is greater than 5. The probability x is greater than 5 is equal to height times width of the little box. Height is 113 and width of the little box is 5. How did I get that? For a total of 5 13s. How did I get that? Well, I got that because I used the width formula again. It's the upper minus the lower, but only of the blue box. Hey, maybe I'll write it in blue so you can relate back to the blue. So W equals height times width. Height is 113 and width is, oh, that's not what I meant to do. Width is not equal to height times. I fell asleep for a second there. Width is equal to upper minus lower of the blue area. The upper is 10 and the lower is L or 5. So the width is 5. That's how I got W for the blue area. Okay, so the answer is this one. Now if you're working on problems, always circle your final answer for me, or put a box around it if you like boxes more than circles, just to show me your final answer, okay? The next question now that I've done that, why don't you guys try the next one, or tell me what did you get for the next one? You can write it in the chat. Maybe I'll make it, I'll go this way. And I wonder if I can take that off. Probably not. So what's the answer to this one here? I'm just waiting for you to respond. What would be the answer of this area? That should be height times width. Height is still 113 and the width here is 3. If you have any doubts, use the formula upper minus lower. So 0 minus 3 is 3. So the width of that space we're going to refer to as so the probability that I'm interested in now is the probability that x is less than 0, the negative values. It's also going to be height times width. To avoid making it more complex, I'm just going to use the same formula. So height is always 113, and this time the width is going to be 3. So the answer is 313. It's smaller, it's less, because it's less of a width, less of a range of values. Okay? So these it looks like I'm answering questions for normal distribution when I write this. I'm not sure there, okay. When I write this and this, but I've already defined that x is uniform, so I don't have to, there you go. So I don't have to explain anymore, okay? Remembering we're dealing with now a continuous distribution. That's why I don't add up all the possible outcomes, because between -3 and 0 is a whole range of outcomes. So instead I use the symbol to denote the possibilities less than 0, and because I know x is uniform -3, 10, I know all the possible outcomes. They end at -3 and they end 10. Okay, so we've done this answer. This is it. That's all of the answer. You could put that in your calculator to get a decimal if you want, but it's not required for this problem. Any questions? Okay, so do as many exercises as you can to know what you need to be what you need to be doing. Okay, because there's a lot of different approaches, but it depends on what kind of variable. Is it a discrete or continuous? Go back to Unit 4 if you have any doubts about how to handle the situation, how to compute probabilities. So you're doing estimation. That's what you're doing. I'm giving you the information about the possible outcomes and the probability of certain outcomes, or probability of outcomes. So I'm giving you the probability distribution, and then I'm asking you to estimate the likelihood of certain outcomes. So we've dealt with all of this so far. Let me know if you have any questions about this. And that brings me here. So I asked you to try problems 1 and 2 to prepare for class. The answers are in the notes. So you do have the answers, but maybe you didn't understand it. So I will solve them. All right. This is actually not so bad to do on an iPad because I can erase very easily. The first question is about these two boxes. So what's going to happen is we're going to conduct random selection from the first box and then random selection from the second box. And we're going to define the variable of interest, the random phenomena, as the outcome of drawing from two boxes. This should feel like, if you feel anything, you should feel that this is something like the gender and occupation variable, where I combine two possible outcomes or two variables in a joint distribution. So that's what we're going to create here. Okay, so you should have a sense about this, but maybe you don't know where to start. When I give you two variables, do what I did in the gender versus occupation exercise. Make a matrix, create a matrix, okay? So let's do that. Let's create a matrix of all the possible outcomes, and that will help us define the sample space. Okay, so we have to distribute each of the possible outcomes as though they show up in pairs. And so all possible pairs. So let me add a page. And what I'm going to do is define box 1. Actually, I'll call this one box 2. The habit is always to put the first variable on this side, and the second one here. That's like kind of like x and y in a way, right? Because, well, not really. That's confusing. But the values for box 1 will go in the rows, so it's kind of horizontal, and the value for the box 2 variable outcomes will go in the columns. So that's kind of like the vertical axis. Anyway, so the possible outcomes from box 1 are 1, 2, 3, 4. Let me make it. I'm going to move this up so you can see everything. 1, 2, 3, 4, 5. So as I said, the answers are in the notes, but maybe you need to see the illustration. And then for box 2, it's 1, 2, 3, 4. All right, that's my matrix, all possible outcomes. So reading from the row first, let's go for this row here. So in all of these instances, the first box, and I'll put some, and divide it like that. The first outcome will be 1, and the second from the second box will be 1. The next possible outcome is 1 and 2, and so on. You get the hang of this, I hope, if you've worked with matrices or linear algebra. Continue. The first box outcome is 2, and the second box outcome is 1, and then 2, 2, and then 2, 3. So fill this all in. 2, 4. And don't do this rudimentary. Don't just do this like blindly, or don't fall asleep doing this. Really think about what's going on and what's not going on. It's going to help you be a proactive learner. So for 1, when have you seen this before? You're going to see variations of this problem. There you go. All right, those are the possible outcomes. It's not pretty. What I could do is I created all the possible outcomes by using the matrix structure, but I could also, and I think it's in the notes, the solution set in the notes, that we refer to the sample space as S, but we use a curly bracket. That's a curly bracket. And you just show 1, 1, or you could do pairs like this, 1, 2. How you put them in is not so important as distinguishing them, explicitly referring to them. I'm just repeating the matrix here to avoid confusion. So again, you're going to see many examples like this. Okay, so finish it yourselves, or check what you're doing. Check that you did this right. Let me put this up. You put all those, the punctuation in. 4, 3, 4, 4, and then finally 5, 1, 5, 2, 5, 3, 5, 4, and with a closed bracket, a squirrely bracket. Okay, so those are all the possible outcomes in the sample space. Because the outcomes that you consider their probabilities must sum to 1, and there's no reason that any one outcome is more likely than the other. The way we've defined this is just the outcomes. They're all equally likely outcomes. So in that case, there are 5 times 4 outcomes, so 20. So 20 possible outcomes translates into there's 20 possibilities, each with a probability of 1/20th, because neither or none of them are more likely than the other. I'll just write it like that. Okay? So each one has a 1/20th chance. Now, let's save this. Let's go back to the problem. Okay, so what did we do so far? The outcome of interest is the set of numbers on the two balls that are chosen. From the two boxes, what is the sample space? So we did that. It's done. So we showed the possible outcomes. That was the sample space, the outcomes, and their probability, 1 out of 20 each. Now, new variable. Okay? New variable that we define as x, the sum of the numbers on the two selected balls. So this is the keyword. You're not just going to represent the outcomes and just give me the outcomes, but you're going to sum them together. We're going to convert them into a new variable. Okay, so this is a combined, or what did I call it? Compound event, in a way. I'm using the outcomes and I'm putting them together, and you'll see how that plays out with the matrix. So I'm going to convert the matrix into a new matrix. So this is my matrix. No comments, guys? Nothing to tell me? I didn't do anything confusing so far? You're very quiet. So yeah, there's going to be a quiz on this. And solve all the problems in the up to the assignment and the homework that's on Moodle. So these are all the possible outcomes here. I'm going to create a new matrix from which I'm going to derive my new variable. Okay, so what I'm going to do is sum these two things. So my new matrix is going to be I can just write 1. It's going to be less messy looking, except I need a better line. So 1 plus 1 plus 1 is 2. 2 plus 2, sorry, 1 plus 2 is 3, and so on. 3, 4, 5, and then 3, 4, 5, and 6, and then 4, 5, 6, 7, and then 5, 6, 7, and 8, and then 6, 7, 8, 9, and let's see, I'm going to make it smaller. You can see it. There it is. So those are the possible outcomes, but I'm not finished yet because I want to create like a list, like the curly bracket list. But more than that, we're going to create the table, the probability distribution, all the possible outcomes and their probability. So what are the possible outcomes? Well, they're here, but there's more than one unique outcome, you see, because there's just 1, 2 there, but there's 3 is possible 2 different ways, and 4 is possible 3 different ways, and 5 is possible 4 different ways, etc. So what I'm going to do is identify okay? Those are the possible outcomes. So X can be, so this is the fun part. Let's define X in words first. x is the sum of the two balls. And then we can make a table with little x, right? Because that represents the values. And then here, the probability that big X takes the value little x. And the possibilities are 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so this looks a little different because we did something different. 2, what's the chance that 2 happens? Well, we're just combining those unique events where each outcome was 1/20th. So if we're interested in 2, 2 happens with 1/20th chance. So the probability of 2 is 1 in 20. The probability of 3, however, has a larger probability because there's 2 ways you could see 3. And each way has a 1/20th chance. So that means that 3 is possible with a probability of 2/20ths. What about 4? 4 is a possibility with probability, it's possible with probability 3/20th. 5 is possible with a chance of 4/20th. 6, also 4/20ths. 7, 3/20ths. 10, 8 is 2/20ths, and 9 is 1/20th. And you guys can't see that, and I just realized I got carried away. So this is what I have. So if you're just watching the video, stop the video and see if you can fill in, or you fill in your table properly. And usually I place this like this, and I say total. And the total is 1. If you add them up, you'll see that 1 plus 2 plus 3 plus 4 plus 4 plus 3 plus 2 plus 1 is 20. 20/20th is 1. Okay. Are we done? Let's go back and see the question. Let me save this. Don't you guys love statistics? I hope so. You gotta love it, at least till the end of semester. It'll encourage your effort and your enjoyment in the time you take putting effort into this. So back to the statement. So here's the question. Let x be the sum of the numbers of the two selected balls. Find the probability distribution of x. We did it, so we're done. Part C. Define the following events. Aha, more combinations, right? Combined events. So A is ball drawn from the first box has an even number. B is the sum of the numbers is odd. And C is the sum is 9. So let's find those events and their probabilities. So these are combining the singular events of summing the balls can help us. So A was the first ball was even, right? That's what it said. Let's see this again. A is the ball from the first box was even. So first box is even in this row and this row. So these possible outcomes here, the red, would be A. Now it's probably messy looking at all of that, so maybe I'll recreate this down here, if you don't mind. So sum again is 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7, 8, 6, 7, 8, 9. Okay. And now for event A, I used red. All of these are the possible outcomes of event A. So what's the probability of A? Well, I'll stick with red. The probability of A is the probability of all those unique outcomes. So those are using now the rule for disjoint events, because if you're just looking at the outcome of of taking a ball from both of the boxes, so just 2 balls summed, then with each equally likely, that's 8/20. That's it, 8/20. So we use what we learned before to help us. That's A. B, event B is defined as the sum is odd. The sum is odd, we'll use blue for that as above. So as above, the sum is odd. The sum is odd here. The sum is odd here. The sum is odd here. And the sum is odd here. So how many events, singular events, does that make, since they're all disjoint, because you can only get one of these at a time by adding the outcome of picking a ball from each box. That's going to be, let's see, 1, 2, right? 3, 4, 5, 6, 7, 8, 9, 10. 10 possible outcomes. Well, it's half of them. So 10 out of 20. So that's going to be 10 out of 20. Now leave it as fractions. You can make it 50% if you want, but I'm going to leave it as fractions. There's one more. There's C. C was just the probability that the sum of the balls is 9. Let me verify that going back. Sum is 9. What's the chance of that? Well, I see that outcome here. And let's put it in black. So probability of C is just 1/20, because it's one possible outcome. Okay, so distinguishing between simple events and compound events. There you go. Alright, so we're done. Question with colorful pens. I'm done answering the second part. It just keeps on saving because the last few classes my computer crashed. It was very annoying and I had to backtrack. Alright. So that's what we did. We did C. This is actually the third part of the problem. Alright. Now, we're at the end. So you see, if this was an exam question, you got most of the points already. Pretty straightforward. The next part, once you do it, and once you do it and get it, you can repeat this with other problems. find the probability of A and B. All right, so now I'm considering these as two events. You can think of the Venn diagram. And what I want to know is, do these events overlap? Is it the case ever that the first ball drawn is an even number and that the sum turns out to be odd? Does that ever happen? That the sum is odd and the first ball was even? If so, identify the outcomes that make it so and their probabilities, and that will give you the probability of A and B. All right? So let's go look at our diagram or our matrix to see when that is the case. So it's that A and B happen. So where's red and blue happening together, right? I should get another color, see if I can get a highlighter. That is not what I want to use. This is a highlighter? No, that's an eraser. It's funny that I only have 3 colors. I am going to use a square. So is it ever the case that you see red and blue, the colors? Well, yeah, right here, right here, right here, right here. Those are intersecting events. So let's put a square around them in red. That one, that one, that one, and that one. So there's 4 places, 4 outcomes where A has happened and B has happened. Okay, so those are A and B. The probability is 4 out of all 20. That's the probability. You can simplify that. I'm just going to leave it like that. The subsequent question is, after you found it, and we'll work with those other ones in a moment, determine whether each pair of events is disjoint or independent or neither. So another word for disjoint would be mutually exclusive. They share no common outcome. Independent or neither. So how would I figure this out? Well, the only way they would be disjoint if the question A and B was asked is if A and B was 0. So they're not disjoint. They actually are outcomes of the overlap. So let's check independence. Now, the other day I taught you how to check for independence. Let's use that same technique. A and B are independent if the statement is true. Okay, if this is true, then A and B are independent. So we're going to check. We're going to use the left-hand side. Remember, LHS is left-hand side. Left-hand side, A and B, we already have that. I illustrated and showed you where I got that from. Left-hand side is actually 4/20. What about the right-hand side? Well, the probability of A I calculated and the probability of B I calculated above, remember? Let's go look at those. The probability of A was 8/20, 8 out of 20, and the probability of B was 10 out of 20. So let's put them here and simplify. So this one was 8 out of 20. and this one was 10 out of 20. So you can do the math, you can do it as decimals, whatever the case. If you simplify this, so this and this gives 1 out of 10, and then this and this gives me let's leave it with the 10, that's the best way. 4 out of 10. Again, you can do this with decimals if you prefer. I just want to show you that this reduces to 4 out of 20. So it is true. Well, there's the colors. I can change them. Okay, so this is 4 out of 20. I'm rediscovering my iPad. I haven't used it for a while. Okay, so it's true. It's true, they're the same. So it's true, they are the same. And you can say, since the left-hand side is equal to the right-hand side, A and B are in fact independent. Okay, it satisfies the criteria for independence. So A and B are independent. So it means, what does independence mean? I just did this algebraically, I just did this mathematically, but let's not lose sight of what we're doing. What does independence mean? Independence means that if you see one outcome, it doesn't change the probability of seeing the other outcome. The probability of the outcome stayed the same. Now let's see what that looks like here. Let's look at A. A is the red. Okay, so the probability of being here, we said, was 8 out of 20. There's 8 possible outcomes. If I'm in A, so if I'm just in the red ones, given I'm in the red, what's the chance that B happens? So I'm already in the red, and out of the red, B happens in half of the places, you see? So B has a 50% chance within A, and B had a 50% chance in general outside of A, in the general matrix. So the chance of B didn't change. It retained its probability. The fact that A happens, or I'm in the red, doesn't change the chance of seeing B. That's independence. Okay? So in other words, let's put it in the framework. If I've seen an even number in the on the first ball, the chance that the sum is odd is still 50%. That's what it says. Okay, I hope you can review that and convince yourself I did that right. I'm going to leave the rest for you to look at. If you have questions, if you want me to continue with the other problems, the remaining problems here for A and C and B and C, I can continue that tomorrow. Also, I wanted to do number 2 tomorrow. And what else I want to do is I'll answer your questions. Send me the problems you want me to solve. If you want me to solve these ones, I think it's pretty well laid out in the solutions. So read these solutions, okay? In general, try all these exercises before tomorrow's class. And what I'm going to do tomorrow is start with conditional probabilities. Conditional probabilities in Bayes' rule. And then this is going to be very interesting in the context of the coronavirus. And then I think I will leave this material for, well, let's see how much I can do on this material tomorrow, but I think I'm going to leave this for Friday, Thursday, Friday. I'm going to do a presentation on Thursday and Friday, so I should be able to finish it this week. Okay, but the quiz then will include everything up to here. The quiz on Thursday will be everything including the Bayes rule. And we're going to finish Unit 4 this week, so that next week I can begin Unit 5. Alright, so I'm going to stop here. Let me know if you have any questions. If you want me to solve any problems in particular, please keep up with your reviews and stay current with my videos. Don't let them build up. I know you have a lot to do, but I'm trying to spread it out into hour videos, so little nuggets of information are being consumed over time, and you have time to assimilate the information, synthesize what you've seen. So we'll talk tomorrow. Have a really great night, and send me your questions.